In the last class, we have understood about the characteristic of the transistor. Let us see an example as to how we can bias a transistor in the active region. IE naught for the BJT that we have chosen is 10 to the power minus 12 amperes, and alpha is 0.995. This is the characteristic that is given by the manufacturer. Let us say bias the transistor at an IEQ of 1 milliampere and VCEQ of 5 volts. So the operating current is given and the reverse bias voltage that we have to apply also is given. Supply voltage is 10 volts. So let us look at the circuit. Supply voltage is 10 volts. Then I put an RC, okay, so as to adjust the collector voltage to 5 volts with respect to emitter. So here the collector current will be flowing ICQ, and therefore this voltage V naught Q is supposed to be 5 volts. This is 10 volts minus ICQ times RC. Okay. And ICQ is already known to be alpha times IEQ. Alpha is 0.995, IEQ is 1 milliampere, and therefore this is 10 minus 0.995 milliamperes, okay, into RC. So if this is given, then we can find out what should be the value of RC in order that this condition is satisfied. This should be 5 volts. So we have from this equation 5 equals 10 minus 5 is equal to 0.995 into 10 to the power minus 3 into RC, or RC is 5 by 0.995 kilo ohms. So this is equal to 5.025. 5.025 K. So we have now found out the value of RC in order to make the VCEQ equal to 5 volts for the transistor that is given. Now we have to find out what VBEQ should be, VIQ or VBEQ. Okay. How much is this? In order that IE is to be made equal to 1 milliampere. This we can look at here. The equation IE is given as IE naught exponent VBEQ by VT. This is known, the diode equation. So VBEQ is VT log IE by IE naught from this equation. So VT is known to be 26 millivolts, 26 into 10 to the power minus 3 log of 10 to the power minus 3 divided by 10 to the power minus 12. This is given here. IE is 1 milliampere and this is 10 to the power minus 12 amperes. So 26 10 to the power minus 3, this is 9 into 2.7 approximately. So this is coming out as 0.632 volts. So this voltage here has to be 0.632 volts. So this is going to be 0.632 volts. As I already indicated that this is typically between 0.5 and 0.7 volts. So now for a given transistor we have found out that it is 0.632 volts. Now how do we bias this? Obviously I should now apply a voltage, DC voltage, which is 0.632 volts. Now you can see here this particular thing is already 10 volts DC, which means actually there is a DC voltage 10 volts with respect to the common point, and another supply which is 0.632 volts. So this is not a nice thing to happen because, right, we require two supply voltage, one is 10 volts, that is easily obtainable, but this 0.632 volts is difficult to get. We can derive of course 0.632 from 10 volts, but it is not going to be an ideal battery, it will be a battery in series with the resistance. So, it will be non-ideal. So, how do you really get a battery of this exact voltage? It is very difficult. If I say the transistor is different, then this voltage may be for 10 to the power minus 13 amperes or so, this may be some 0.7 something. Okay. So, that means this is very sensitive, the current here is very sensitive to this voltage. If I am not able to make it 0.632 and if it just drifts to 0.631, then the current is going to be drastically different from 1 milliampere. That is because the current and this voltage, they are exponentially related. And therefore, the biasing by using a voltage like this is very unstable way of biasing a transistor, because this voltage and this current, they are very sensitive to one another, and therefore, this voltage, small variation in this voltage will cause a large variation in this current. So, biasing this in a stable manner by using a voltage source here is very difficult. This is unstable way of biasing. Then how do I really bias this? I know that I have to have 1 milliampere of current here. If alpha is 0.995, then beta of the transistor, which is alpha by 1 minus alpha, is going to be 0.995 divided by 1 minus 0.995. This is 0.995 by let's say 005. So, this is going to be equal to, how much is this? 199. So, you can see beta is very high. What is beta? Beta is the ratio of IC and IB. This is equal to beta. So, this is given as 199. So, for a current of ICQ of 1 milliampere, what is IBQ? That I can find out. 1 milliampere divided by 199. Okay. So, this is the current which is going to be of the order of microamperes. How much is this? This is going to be, this is really 200, and therefore 1000 divided by 200, okay, which is 5, around 5 microamperes. So, approximately about 5 microamperes. So, it is enough if I fix the current as 5 microampere for this transistor in order to make the emitter current equal to 1 milliampere and collector current equal to 0.995 milliampere, instead of bothering about this voltage. So, an alternate way of biasing this is, instead of using this, right, 0.632 volts, I know that it is 0.632 volts, okay. I will now bias this such that this 0.632 volts is got by a current, and that current can be how much? About 5 microamperes. Then automatically this will be 0.632 volts. So, how do I make this 5 microamperes? Okay, I will try to use the same supply, put a resistance RB in series with it, and put the same supply, so that I can use same 10 volt supply both for reverse biasing the transistor by 5 volts as well as forward biasing the transistor, okay, so that 5 microampere current flows. So, this is 10 volts. So, now the problem is, given that this is 10 volts, which is the same supply as that, I have to find out RB in order to make this current equal to 5 microamperes. That is very simple. So, this is 10 volts minus 0.632, that is the drop across RB, that divided by RB should be equal to this voltage minus this voltage, that divided by RB should be equal to 5 microamperes, or RB is going to be equal to, this is going to be 863, okay, 9.368, okay, divided by 5 mega ohms, right, mega ohms, which is how much is it? 1.87 mega ohms. The problem therefore illustrates, okay, classically how biasing for this transistor is done in a simple manner by fixing the base current here rather than fixing the base to emitter voltage. Right. So, what does it mean? This circuit, if I redraw the circuit, this RB is connected between base and this positive terminal of the 10 voltage, 10 volts. So, I will redraw the circuit. So, this is RB. So, this is a single supply biasing of the transistor in common emitter mode. Okay. It has to use two resistances, one to fix up the reverse bias voltage RC and another to fix up the forward bias current as IB. Okay. So, you can therefore bias a transistor like this by using RB and RC in common emitter mode. Emitter is a common terminal between the output and the input. Okay. But this also is not a very stable way of biasing. What happens here is, as long as this is 10 volts and this is about 0.6, this current is continuing to be, okay, this 5 microamperes. This will remain constant. That is what we have fixed. But beta for different transistors will be differing. Okay. For one transistor it may be 0.995, another one it may be 0.996. That means beta is going to be different for different. If it is 0.99 for one transistor and 0.995 for the other transistor, the beta is going to change from 100, that is 200 to 100 very nearly. So, that means if, for example, beta changes because alpha changes from very small amount 0.995 to 0.99, you can see that beta changes, okay, from 200 to 100. So, the current here, if it is fixed for a beta of 200, okay, then it is going to be double that, okay, or if it is fixed for a current of it is 200, then it is going to be half of it for beta equal to 100, or if it is fixed for 100, beta equal to 100, it will be double for 200. So, the current IE is going to be very sensitive to beta variation here. Okay. So, this kind of thing should not happen in again a biasing circuit. So, what should you do? This is not again that stable a way of biasing. Fixing IBQ is not good. What should be fixed is IEQ itself, and that can be done in the following manner. So, I do not want to fix this current, but I can fix IEQ. I will fix the reverse bias voltage using this supply and RC, but now I will decide to use another supply, okay, for forward biasing, independent supplies for forward. then that will fix the current in the emitter. This voltage is going to be already we have fixed as point, how much is 632, but now it is negative. So, if I ground this base, connect it to ground, make that common, and apply a negative voltage of 0.632 to emitter, then again it is biased according to what we require. But again getting 0.632 negative voltage is very difficult. Instead, I can get an emitter current of 1 milliampere by putting an emitter resistance Re, and let us say we will use a supply voltage which is negative here, but equal to 10 volts. So, minus 10 volts is what is going to be used with respect to ground here, and plus 10 volts here. So, this is using dual supplies. So, now you are fixing the emitter current. So, it is going to be 10 minus 0.632 divided by Re. This has to be made equal to 1 milliampere. So, now this voltage, okay, minus this voltage divided by Re is the current in this. Okay, this is negative, it is minus 0.632, minus 0.632, minus of minus, that is plus 10 volts, divided by Re, that is the current, that is equal to 1 milliampere. And therefore, now what happens? Re gets fixed as again 8, 6, 3, 9 K, 9.368 kilo. If that is fixed, then now look at it, irrespective of the transistor beta, since I am fixing IE itself, okay, the base current will have to adjust itself. As beta changes, base current will change, that is of no consequence. Emitter current remains constant. So, this is a stable way of biasing a transistor. So, if emitter current is fixed as 1 milliampere, collector current has got to be 0.995, okay, times that, or 0.99 depending upon the alpha. So, whether it is 0.995 or 0.99, it is very nearly 1 milliampere. So, it does not really matter, okay. Even if alpha changes, or even if I use different transistors belonging to different manufacturers, the current here essentially remains constant at about 1 milliampere. So, this is a stable way of biasing. So, we have now understood 3 ways of biasing a transistor in the forward direction. 1, just apply a voltage of 0.632, keep the emitter grounded, apply a voltage of 0.632 positive to the base, which is very sensitive, okay. That is, emitter current is very sensitive to this voltage. So, if this voltage changes even slightly, it will change drastically, and this voltage of 0.632, it is difficult to obtain, okay, exactly. So, instead we ground this and connect a base resistance and apply it to the positive voltage 10, so that the base current gets fixed, in which case collector current or emitter current will be dependent upon the base current, since the base current is fixed, and base current for this problem with 0.995 alpha is equal to 5 microamperes, and I fix the base current as 5 microamperes by putting an appropriate base resistance and connecting it to 10 volts. That also is not a very satisfactory way of biasing, because if alpha changes from 0.995 to 0.99, the emitter current will change to half the value. So, now Re, if we introduce with another supply voltage, this base is grounded. Now, you have to apply minus 0.632 here. That is also not a good way of biasing. Instead, I will use minus 10 volts, whereas I have used plus 10 volts for the positive, a dual supply, and then put a series resistance of Re in the emitter to fix the emitter current as 1 milliampere. which is a very stable way of biasing. That is, even if the transistor is changing, okay, from this type to another type, or transistor beta itself changes, okay, due to different temperatures, etc., then the collector current essentially remains constant at 1 milliampere. So, now let us understand the important aspect of biasing a Bjt amplifier. A Bjt works as an amplifier, we have understood, if base emitter junction is forward biased and collector base junction is reverse biased. So, let us consider a very simple arrangement where applying a single supply VCC, let us say, and in series with that RC and collector, we can make IC flow through this and bias this at VCE equal to VCC minus ICRC. So, that takes care of the reverse bias. And as far as forward bias is concerned, we have to forward bias this base with respect to emitter by an extent VBEQ, depending upon what current we want through the transistor. This is the emitter current. So, now emitter current and base to emitter voltage, they are related, okay, approximately by this relationship IE is equal to IE naught exponent VB by VT. Actually, that minus 1 has been ignored. Okay. So, IE is equal to IE naught, which means this is the characteristic. You can see that it is following a characteristic like this. Up to this, the current is essentially going to be almost 0, and thereafter current increases enormously. This is what is interpreted by this equation. What it means is that it is very crucial, if I am fixing up VBEQ, if I want a certain IE, okay, I want to operate at this IEQ, then I have to exactly know what this voltage is. Even if it is slightly different, this current is going to be maybe very low, or if it is slightly higher than this, it may go to very large current. And this is going to be causing problem, right, in terms of, for example, let us say I want an IEQ of let us say 1 milliampere for this, and VCC is, okay, 10 volts, okay, and the resistance RC is 5K. So, 5 volts comes here. This is the example which we had just worked out. 10 volts was VCC and 1 milliampere was the current, and 5K was the resistance here, so 5 volts. It is exactly set in between, okay, 10 volts and 0 volts. So, nicely active device has been operated at a midpoint of the 10 volts and 0 volts. So, it can swing around that. But suppose this VBEQ is slightly higher, then let us say the current actually should have been 10 milliamperes according to that VBEQ. But then if you had put 10 volts and 5K, the maximum ever current in this is going to be 10 divided by 5K, which is 2 milliamperes. That means it cannot work at any current greater than 2 milliamperes, which means if you are putting a VBEQ which is greater than that can cause a current of 2 milliamperes, the transistor will automatically go to saturation, because it cannot satisfy the transistor equation which says IE should be equal to alpha times IC should be equal to alpha times IE. This is not valid. So, which means for any voltage which is greater than that exactly specifying voltage that is here for 1 milliampere, this may go to saturation. It will not any longer work in the active region. So, this way of biasing is no good, fixing this voltage here. So, for that purpose we said we will make a base current flow through this corresponding to IE. If it is 1 milliampere, the IB is going to be IE divided by beta plus 1. That is because IC is equal to beta times IB, okay, and therefore IE is equal to IC plus IB. Therefore, we have IE is equal to beta times IB plus IB, or it is equal to beta plus 1 times IB. So, if I therefore fix the base current as IE divided by beta plus 1, suppose emitter current is given as 1 milliampere and beta is given as, let us say, 199, then 1 milliampere by 199 plus 1, 200, which corresponds to about 5 microampere, is what I have to fix as base current. It is easier to do this, okay, than to find out what VBEQ is, and that we found out as about 0.632. Okay. If it is even different from this by about 1 millivolt, current will be drastically different. So, we will fix the current of this as IE by beta plus 1. How do I do that? I will now put another resistance which I call as RB, so that this current in this is nothing but VCC minus VBEQ, which I already know for that current, okay, divided by RB. This resistance VC minus VBEQ by RB is this current. So, this is an important equation for biasing a transistor this way. So, the forward bias is fixed this way, okay, by fixing the current rather than the voltage. If I fix the current, automatically VBEQ will adjust itself, okay, so that that current flows as a base current. Then if that current flows as a base current corresponding to 0.9995 or 0.99, depending upon the alpha, the emitter current gets fixed. So, this is the way of fixing base current. What do you mean by base current is fixed? This is now determined by you. This is VCC minus VBEQ, which you can typically take as 0.6. There will not be much of an error, right, divided by RB. So, that will forward bias this junction, and automatically we have the reverse bias fixed by this VC equal to VC minus ICR. This is one way of biasing a transistor in common emitter configuration. Emitter is common to the input as well as the output. But as I told you, if you fix the base current as this value, then the emitter current or collector current, which is what we want, is going to be beta times VCC minus VBEQ by RB. So, it is sensitive to variation in beta. So, this is not a very good way of biasing. We have desensitized as far as IB variation, okay, is concerned. IB is made very constant because VBEQ, okay, small compared to VCC. So, this is VCC by RB itself, okay, approximately, but still this is sensitive to beta variation. So, this is not a good way of biasing, even though this is a way of biasing. Okay. Then the alternate way of biasing, as I told you, which we have already discussed in the example, is not a common emitter configuration where base is made common. Okay. Then we have this still coming into picture. This is VCC. This is still, this point with respect to common point is still VCC. So, VC equals VCC minus ICRC, that is still valid, that is collector voltage, not VCE, okay, the collector voltage with respect to common point, whatever it may be. And emitter voltage now has to be negative because it is VBEQ, base is made common. With respect to base, all the DC voltages and AC voltages are measured. So, base is common. Now I have to necessarily use, okay, a negative voltage, because this is a positive voltage with respect to base, right. So I have to use a negative voltage. That means I could use VBEQ, which is negative, appropriately chosen, so that this current is there. But again, that is a bad way of biasing, because that VBEQ may not be exactly known. So I put a resistance here and connect it to what we call as VEE, call this negative minus VEE. So this resistance we will call as a resistance put in the emitter to fix the current, which is emitter current, as equal to VEE minus VBEQ divided by RE. So we have minus VBEQ minus of minus VEE, right, that is plus VEE divided by RE. So this is the emitter current. So here this is the circuit in which emitter current is fixed. If emitter current is fixed this way, what is collector current? Collector current is going to be now alpha times, okay, the same expression VEE minus VBEQ by. Now you compare this with the earlier one. In the earlier one, the collector current IC was beta times VCC minus VBEQ by RB, and beta is very sensitive, okay, to temperature and the device, whereas alpha, even if it changes from say 0.99 to 0.995, it is very close to 1. So collector current does not change. Whereas when alpha changes from 0.9 to 0.99 to 0.995, beta will change from 100 to 200. Right? So that is very sensitive, whereas this is not so sensitive. So if you want the bias to be stable, why do you want the bias to be stable? Because whether it is this transistor with this value of beta or some other value of beta, I want the operating point to be in the active region of interest to me, right, not go to saturation or something like that. So if emitter current gets fixed as 1 milliampere, okay, collector current is very nearly 1 milliampere, irrespective of the transistor I use. Okay, for a supply voltage of 10 volts and RC equal to, let us say 5K, it is going to remain the same, right, the reverse bias and the collector current essentially remain the same irrespective of the transistor, whereas that is not the case with this arrangement of biasing, where the base current is fixed. So this is a bad way of biasing, this is a good way of biasing. But what is the penalty? In this case you are using a single supply, in this case you are using dual supply. But we can have a compromise between this and this by using essentially both base resistance and emitter resistance. Suppose I decide that there shall be base resistance as well as emitter resistance, then I have a choice possible, okay, in biasing this circuit. So we will go next to that way of biasing using a single supply, which can still be made stable. Okay. So essentially we have discussed two extreme situations. This is common emitter biasing scheme, this is common base biasing scheme. Base is the common point for the DC voltages as well as AC. Here emitter is the common point. Here you can manage with single supply, we have to have dual supply in this case. Just now we said making the base common, okay, we can use a negative supply and a positive supply. Okay. The positive supply to reverse bias and negative supply to forward bias. This NPN transistor. So, I have essentially redrawn with these batteries actually put there instead of indicating minus and plus as previously, right. This is just to depict that this configuration within this loop has VEE and RE and VBEQ within this loop. Okay. Within this loop, of course, it has VCC, RC, RE and VEE. Okay. So, anyway, this battery forward biases this battery reverse biases this. Now, this arrangement essentially can remain as such as far as this loop is concerned. If I put this battery, okay, instead of here, I will put it, this should be positive and this should be negative, okay, and short circuit this. So, as far as this loop is concerned, nothing has changed. In fact, it will be VEE, same VEE. So, the equation is at the input going to be the same as previously written, VEE, okay, minus VBEQ divided by RE is still the current IE. Only thing is, in this VEE which was earlier present is absent, that is all. So, now you can see that I can therefore still bias in a stable manner, okay, using two power supplies, okay, but these two power supplies have to be necessarily different, because this is VEE, an ideal supply, and this VCC has to be obviously greater than VEE, because this collector potential should be greater than the base potential here, right. So, I cannot use for this VEE same voltage as VCC here, that is a problem. So, VEE here has to be less than what? VCC minus IC times RC, that is the collector potential. In order to reverse bias the transistor, this VEE has to be less than VCC minus ICRC. So, if I cannot use dual supplies, saying that this is 10 volts and this also shall be, okay, minus 10 volts, and just put that minus 10 volts as plus 10 volts. That will not work here, right. That is because I require a reverse bias voltage here. So, for this reason, therefore, I can still use this supply in order to derive a supply which is less than VCC. By Thevenin's equivalent, I can now so if I now see the voltage here, open circuit voltage, it will be R1, okay, by R1 plus R2 times VCC. So, I can get any voltage which is still positive and less than VCC minus ICRC by appropriately selecting R1 and R2. But the only trouble is, this is the Thevenin's voltage here, but there is also a Thevenin's resistance in series with this Thevenin's voltage the moment I use R1 and R2, which is equal to R1 parallel R2. So, this R1 parallel R2, we will call this as RB, okay, and this Thevenin's voltage as VBB, okay, is what is going to appear here if I connect it up this way, which means this is equivalent to, right, a battery which is VBB of magnitude this way, VCC into R1 by R1 plus R2 in series with R Thevenin's or RB, now we are calling it, which is the same as Thevenin's equivalent resistance, which is R1 parallel R2. So, it is not an ideal battery as envisaged here, okay. So, there is a series resistance RB. Actually, we would like to have RB as 0 in order to do the stable biasing, but it is not so. So, let us see how this compromise circuit will work. So, I am removing this battery VEE and replacing it with this kind of arrangement. So, instead of a battery with the emitter resistance, I have a battery in series with RB, okay, which could be made as small as I please, because that is my choice by selecting R1 and R2 appropriately, and then this RE. It is a must that RB should be very small compared to what? This is important. That means the voltage here should be essentially VBB. The drop in RB should be negligibly small. What is the drop in RB? The drop in RB is nothing but IB times RB, because IB is flowing this way. So, actually speaking, the voltage VB is going to be equal to VBB minus IB times RB. So, this should be very small compared with what? Okay. This drop comes here, okay, and that is now going to be essentially VB, okay, and this is going to be dropped across this as well as this, okay. So, this is going to be equal to VBEQ plus the drop in this IE times RE. So, in order that we have a stable biasing as envisaged earlier, this should be small compared to this IE RE, right. That means IB RB should be much less than IE RE. This is a stable way of biasing. Have you understood this concept? Right? That means if IB RB is much less than IE RE, I can ignore this, and essentially we have the same equation. IE is going to be now fixed as VBB minus VBEQ by, let us say, RE. The same expression as earlier, right, and IC is going to be alpha times IE. So, how do we select this? We know what is IB in terms of IE. IB is IE divided by what? Beta plus 1. IB is IE divided by beta plus 1. So, this relationship, you can cancel this, and this is an important relationship in biasing, that you must select RB which is going to be much less than RE into beta plus 1 only. That means R1 parallel R2, which is RB, shall be so chosen, that means R1 R2 by R1 plus R2, which is RB, should be much less than RE to beta plus 1. This is easy because beta is very high, right. Suppose RE is of the order of kilo ohms, right. Beta is, let us say, 199. So, 200 kilo ohms. So, R1 parallel R2 need to be much less than only 200 kilo ohms. That means even when R1 parallel R2 is of the order of 20 kilo ohms, this is satisfied, right. So, this kind of design is what is going to work satisfactorily for biasing this transistor in a stable fashion. But now, please see here, nothing is common here, right. Base has been lifted, emitter has been lifted, okay, collector is already lifted. So, base, emitter, collector all at certain DC potential with respect to ground. Okay. So, this is a general configuration wherein we can bias the circuit in a very stable fashion. So, let me take an example. VCC is equal to still let us say 10 volts, and I want let us say VCB equals 5 volts. Okay. I want VCC equal to 10 volts, VCB equal to 5 volts, okay, and IC should be equal to 1 milliampere, let us say. So, design an appropriate circuit so as to have all these conditions, right. The transistor characteristic is not clearly known, which means this kind of biasing should be possible whatever be the transistor I use. So, we have 10 volts being used, example 8, right. So, 10 volts being used, let us put an RC here and IC equal to 1 milliampere. So, what will be the RC, because this, okay, and VCB is this voltage, okay, this shall be 5 volts, okay, this is 10 volts. Now, this is going to be about 0.6 volts, 5.6. So, then I can have an RE which is unknown, and then an RB which is also not known, and VBB for biasing this. This is going to be RC, which is not put, right. So, please, now what is specified is that this is 10 volts and the current IC is equal to 1 milliampere. Then I will take, let us say, alpha as 0.995, let us say simple. That means beta is 199. So, you can say that IC is very nearly equal to IE, right, because alpha is 0.995. So, this, if it is 1 milliampere, this also is going to be around 1 milliampere. This voltage is 5 plus 0.6. So, this is 5.6. This is 5.6, this is 10 volts. So, what is the effective drop in RC and RE? 10 minus 5.6. So, 10 minus 5.6 is equal to 1 milliampere, okay, into RC plus RE, assuming that IC is equal to IE. So, this, in this loop, if you write down the Kirchhoff's equation, 10 minus 5.6 is equal to IC, which is equal to IE, let us say, into RC plus RE. So, we get RC plus RE as equal to 4.4 K. So, let us say we will take RC as about 3K and RE as equal to, let us say, 1.4K. This is now looking somewhat arbitrarily, right. This depends upon what kind of load resistance you should have. So, RC is equal to 3K and RE equal to 1.4K is a solution here. Okay. If you do that, then this is 1.4K and this is 3K. So, 1.4K into 1 milliampere is 1.4 volts drop here plus 0.6. So, this voltage is going to be 2 volts, 1.4 volts across this and 0.6. So, this is at a potential of 2 volts. If I ignore the drop in RB, then VBB shall be equal to 2 volts. So, VBB is now known to be very nearly equal to so you know the Thevenin's voltage. So, once you know the Thevenin's voltage, that is R1 by R1 plus R2 into 10 volts is equal to 2 volts, that is the Thevenin voltage. So, R1 by R1 plus R2 is equal to 1 by 5. So, we have 5 times R1 equals R1 plus R2 or 4 R1 equal to R2, that is another condition to be satisfied. And how do I select R1 parallel R2? That we already know. R1 parallel R2 shall be much less than beta plus 1 is 200 in this case into RE 1.4 K. That means much less than 280 kilo ohms. So, let us take it as 28 or let us say 28 kilo ohm. Anything less than 28 satisfies this relationship, right. So, let us say any resistance which is less than 28 K. So, R1 parallel R2 is, you know, R1 parallel R2 is 28 K, R1 by R1 plus R2, or 4 R1 is equal to R2. Now, you can substitute for R2 here and get the value of R1. So, I will leave it to you, find out the value of R1 and R2 and come to the next class. This is one relationship, this is the other relationship. So, that will fully satisfy this biasing arrangement, and therefore, you can again redraw the structure with R1, R2, VCC, RC and RE. That is the complete structure. So, I would like you to evaluate R1 and R2 and redraw the biasing circuit. In the next class, we will give you the complete circuit. Okay? Please try to attempt this in your hostel.